Good day again. So, this will be part 2. I hope you watched the part 1 of power supply. This is part 2. We're talking power supply. Okay. So, we've got an exercise here. Alright, let me just use a. Alright. Then they say, power supply, a full wave, okay, please, full wave, there we go, bridge, rectify, 2 details, okay, so let me just do this, let me change this to another one, a full wave bridge rectify, full wave bridge rectify, with a filter capacitor, uses a transformer with a turns ratio of 10:1. Alright, if the supply voltage of the transformer is 250 volts at 50 hertz, then they say calculate the secondary voltage. Sharp. So how do we go about doing this? There are things that you need to look out for in this case. Alright, now one of the things that you need to look out for is the following: this transform. Okay, now when you see transformer, okay, but we'll come back to the transformer issue. Let's start first with 16.1. 16.1.1. Let me see. They say calculate for peak secondary voltage. So you know it's V1 over V2, which is equal to N1 over N2. Okay, which one am I looking for? I'm looking for V2, peak secondary voltage, on the other side of the circuit. So, do we have V1? Yes, V1 is 250 over V2, which is equal to 10 divided by 1. Okay, therefore V2 equals to 250 times 1 over 10, which ultimately becomes what? No, something is wrong. It's not 250. Okay, it's not 250. I already have an answer in the mind. Alright, it's 250 times 1 over what? Over 2. Hey, I'm making so many blunders. Okay. My mind is preoccupied by something. 250 times 1 over 10, which ultimately becomes what? 25. That. So one of the things that people constantly make a mistake on is that when they see this, alright, V2, which is the secondary, alright, they say that's the final answer. That's not the final answer. Why? Because of the transformer, there. So what do we need to do? Alright, we need to do what? We need to simply say, alright, once you, let me write it here. If you see, transformer in your statement, okay, that means V out is equal to VRMS. So this 25 here, this 25, right? It's not V peak. It's not V peak. Right? Let me write it here. So that V2 is not equal to V peak. Okay, V peak. It's not. What is it equal to? Instead, V2 that you calculated because of the presence of a transformer is equal to V RMS. Okay, V RMS. So let's go to the table. What's the value of V RMS? The value of V RMS is equal to what? The value of V RMS is 707 of V max. So therefore, alright, we know that our answer is 25. So V RMS equals to 0.707 of what? Vmax. Okay, what is Vmax? So in this case, Vmax is equal to VRMS, it's 25, being equal to 0.707 bracket V peak or Vmax. Alright, so therefore, ultimately, our answer becomes V peak or Vmax being equal to 25 all divided by what? 0.707. Okay, so let me just get the answer. 25 divided by 0.707. The answer is 35,361 volts. There we go. That becomes our there's a phone call coming in. That's our final correct answer. Okay, why did we engage all of this? Why did we engage all of this? It's because they did tell us that this circuit has a transform. That's why we are doing that. Alright, what's the second point? Now, do you see this table here? Let me highlight it in another color so that I don't annoy you. But I like it, man. I like it. Okay, there we go. This entire, alright, do we see all of this? We only use these values if we do not have the value of the capacitor. Alright, if you can check, were you given the value, were we told that there's a capacitor? Yes, there's the capacitor. There's the capacitor. But were we given the value? Alright, let me just do this. Were we given the value of the capacitor? No, we were not. So that means that, alright, we can use these values to determine all of these. Alright, once we get the value of the capacitor, then this will no longer work. This, alright, all of this, alright, all of these details will not work if the value of the capacitor is given, or if the circuit does not have a capacitor. You use this. This is before what? Before filtering. Before filtering. Now I'll show you what what filtering does to a DC waveform. Second one, secondary average voltage. Now I need you to follow. When you talk about V average, you've got V average here. There we go. V average, the second one, the second block. There's your V average. Okay. So under power supplies, V average is the same as saying VDC. That's why they say VDC brackets average. Okay, it's the same. When we say VDC, you're talking about V average. When you say V average, you're talking about VDC. But now, this formula here, it's only applicable. You can only use it if you do not have a capacitor. Okay, or the value of the capacitor is not given. So, VDC bracket average is equal to now we go back. Our statement says what? A full wave bridge rectifier. We come here. Under VDC, what do we have? We do have what? Okay, let me change the color. Under VDC, we do have half wave, we do have full wave. So we need to use the full wave because the circuit is indicated as what? A bridge rectifier. There we go. So that's what we are having in this case. So therefore, when we solve this, we're going to say 0,638 brackets. What's our Vmax? Vmax, don't forget, it's not 25. Here, Vmax, we calculated it. So therefore, it's 35.361 brackets. There we go. And then ultimately, VDC is equal to, alright, then we're going to calculate this. So the answer here is 22,56. Alright, volts. 560. So I'll just omit that 0. So that becomes our solution. So if you did not see the word transformer, okay, what were you going to do? All right, let me use a different color. It's nice to use different colors here. Yes. Okay, let me use blue. Let me use blue. Okay. So if you did not see the color, not the color, the transformer, all right, then you were going to use 25 as it is, and as a result you were going to get V peak wrong, and also you are going to use 25 here. You're going to use 25 here, all right, which also becomes incorrect. Okay, so please be mindful of such things whenever you do those calculations. Cool. All right, what's the other thing? Peak inverse voltage. Now, what is peak inverse voltage? If you're looking for peak inverse voltage, there we go. Okay, peak inverse voltage, there we go. Okay, that's our peak inverse voltage. Okay, so peak inverse voltage, how do we determine it? If it's half wave, you use Vmax. If it's full wave, then you will come to this block here. All right, but now when you check here, we've got two Vmax for center tap and we've got Vmax for bridge rectifier. So let's go back. The second is a full wave bridge rectifier. That means that in my solution, I will simply say because peak inverse voltage, because of it's a bridge rectifier, it's also equal to Vmax. So again, if you did not remember that the transformer is being used or mentioned, okay, that means that if you did not see the transformer part, you would have used 25, yeah, all right, and it would be incorrect. Your V peak will be incorrect, your V average will be incorrect, your PIV will also be incorrect. So therefore, ultimately the answer becomes what? Ultimately the answer becomes 35.361 volts because of the answer that we got there. There we go. So that solves this question on. Now, why are we doing this? We are doing this calculation to show you calculations that take part before we doing filtering. Now let me explain what is filtering in this case. I need to draw first on the same page, all right, so that you can understand what we're talking about. Now, this is Eskom Power. All right, you'll pardon me with the. There we go. Bridge rectifier. Gosh. Yeah, no, my drawing is bad. My drawing is bad. Oh, gosh. I'm trying. Yeah. There we go. Yo, this is a bad drawing, but I'm trying. There we go. Mm, mm, mm. Cool. Cool. So here, I'll push that. That. There we go. Now, guys, after filter, remember what were at this point here. All right, what do you have? You've got a sine wave from Eskom. At this point here, what do you have? You have this. This is what we call pulsating DC. This is rectified sine wave. Now, this was AC, and this one becomes what? DC. Okay, cool. Now, when you bring in a capacitor like this, we call this C1. C1, it has a function. The function of C1 is to do what? Is to smooth. Or to do what? It's to filter. So what do we mean filter? Let me draw it in big. But now, hey, pardon me for my diagram. Alright. This is DC. Okay. When you filter, you start having waveforms like this. Charging, 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 discharge, discharge, discharge. So you end up having a waveform like this, where there we go. Okay, your normal pulsating DC, it touches back here onto 0, but with filtered DC, now you have waveform going up, making a stop there, going up, making a stop there, going up, discharging there. There we go. So your waveform looks like this. It doesn't touch back to 0. This one, what do we call it? We call it pulsating DC. This one, we call it, it's not 100% pure DC. We just call it DC because it does not touch back onto what? Onto 0. So there's the function of C1. C1, it changes this waveform here. It changes and it makes it to be like the one at the bottom of the page. So what do we do whenever we encounter these type of so I'm gonna do another recording where I show you. Okay, I'm going to continue on the same page, all right, and then showing you the effects of C1 into our calculations. Sharp.